Greetings, Math 347 fans. Video here on generalizations of these higher order differential equations. In this section, when we talk about higher order differential equations, we actually really mean higher order differential equations, not just second order differential equations. So we'll go ahead and change our focus from the linear second order differential equation given by this problem to just a general higher order but constant coefficient differential equation. Okay, a few expectations first on these homogeneous constant coefficient differential equations. We'll first reframe our differential equation as an nth order equation. So here's an nth order constant coefficient homogeneous differential equation. Here, again, notation, the parentheses indicates an nth or n minus first derivative. Okay, as you might imagine, we can rephrase our differential equation as Lx equals 0, defining the linear differential operator Lx as the nth derivative plus some constant times the n minus first derivative, and so on and so forth down to some constant p0 times the 0th derivative. This is a linear operator in the same sense it was previously, namely that differential operator applied to the sum is the sum of the differential operators, and similarly you can pull a constant out. Okay, the principle of homogeneous superposition applies to this nth order operator too. Namely, if we have n solutions of this differential equation, any linear combination of that solution is also a solution. And you can see this quickly just by substituting the expression c1x1, c2x2 out to cnxn into the differential equation and using linearity. A few facts, expectations, and terminology. That expression c1x1 plus c2x2 all the way out to cnxn is a linear combination of x1, x2, all the way out to xn. Moreover, if those n functions are linearly independent solutions of the nth order constant coefficient homogeneous differential equation, those functions together in a set form a fundamental set of solutions to the homogeneous differential equation. Now, just like we would expect a two-parameter family for the general solution of a second order equation, here we expect an nth order parameter, n parameter family for the nth order differential equation. We expect to be able to select one of those family members to satisfy a given initial value problem, and of course, given any initial value problem, we expect the solution to the constant coefficient differential equation to be unique on the entire real line. Okay, the general solution to this differential equation follows similarly as long as we can cook up n linearly independent solutions to the differential equation, the homogeneous differential equation. The general solution is a linear combination of those linearly independent solutions. Okay, so again here we're thinking of these guys as forming a fundamental set and smashing them together with some constants c1, c2 out to cn to express the general solution. So again, to sort of summarize that method, the strategy for solving an nth order homogeneous differential equation, linear differential equation, we expect to find n linearly independent solutions. We identify a fundamental set of solutions and then write the general solution as a linear combination of the n linearly independent solutions. So it's exactly what we did before with our second order equation. Just replace 2 by n and you have it. And that's a generalization in this case. Okay, so how do you think you solve this nth order constant coefficient homogeneous differential equation? Just like you did, try a solution of the form e to the lambda t. And similar to our second order case, when you try a solution of the form e to the lambda t, we end up with a characteristic equation, namely lambda to the n plus p to the n minus 1, lambda to the n minus 1, and so on and so forth, all the way down to p0 equals 0. So roots of that characteristic equation are known as eigenvalues of the differential equation, and they correspond to solutions of the differential equation. So for every root, there's a solution. And The fundamental theorem of algebra tells us that this nth order polynomial has exactly n solutions, including complex roots and multiplicities. So we end up with the n linearly independent solutions just as you would expect, right? So for each real distinct root lambda, there's the solution of the form e to the lambda t. For every multiple root, say it has multiplicity k, right, we get the 1, 2, all the way out to k linearly independent solutions multiplying by t, the appropriate number of times. And as you would expect for each complex conjugate root, there's a solution of the form e to the alpha t cosine beta t and e to the alpha t sine beta t. Now there's actually one more case that we haven't included here. One thing that can happen with these higher order differential equations is complex repeated roots. And guess what happens? You might have guessed it. It turns out you just multiply these by a factor of t, the correct number of times, until you have the correct number of solutions. Now, that being said, I won't do that to you, but it's a similar generalization of a real repeated root. For each real or each complex repeated root, you end up with exponentials times cosines or exponentials times sines, and you multiply by t until you have the right number. Okay, so a few examples that sort of illustrate this. Suppose that we have a 6th-order differential equation, and we've identified the eigenvalues of that differential equation. 2 plus 3i and 2 minus 3i are a conjugate pair. 4 is an eigenvalue with multiplicity 3, right? It's an eigenvalue 3 times. And minus 1 is an eigenvalue. Okay, so let's find the general solution of this differential equation. So the first thing we'll do is go ahead and identify the solutions that correspond to each eigenvalue. So corresponding to the complex conjugate eigenvalue, we get solutions of the form e to the minus 2t cosine 3t and e to the minus 2t sine 3t. Corresponding to the multiple root of multiplicity 3, we get e to the 4t, and then t e to the 4t, and the third linearly independent solution there is t squared e to the 4t. And then, of course, corresponding to the real distinct root of minus 1, we have a solution of the form e to the minus t. So when you go count them up, we have the right number of solutions here. We have 6 linearly independent solutions, as it turns out, and the general solution is a linear combination of those linearly independent solutions. So here's a fundamental set of solutions, those 6 solutions in a set, and the general solution I've written here in a couple factored forms, right? So factoring out the exponential from these cosine and sine terms, and factoring out the exponential from the repeated root terms. So the general solution, again, a linear combination of those linearly independent solutions. Okay, a second example. Here we're asked to find any old differential equation with the general solution c1 e to the 3t plus c2 t e to the 3t plus c3 e to the minus t. Okay, so here we see a 3-parameter family of solutions. So we would, in some abstract sense, expect to have to solve a 3rd-order equation to find this 3-parameter family of solutions. So we'll start in investigating this differential equation by sort of breaking down this 3-parameter family of solutions into the 3 components that form the fundamental set of solutions. So hopefully you can identify a fundamental set of solutions corresponding to e to the 3t, t e to the 3t, and e to the minus t. Okay, so together those 3 solutions correspond to 3 roots. One root, of course, is minus 1. Minus 1 is a root corresponding to e to the minus t. And then, of course, there's a multiple root of multiplicity 2 corresponding to the eigenvalue 3. Okay, so we can express the characteristic equation as lambda minus 3 quantity squared. That represents the multiple root of the characteristic equation. And lambda plus 1 represents the root minus 1. So it's pretty quick to multiply that out, and when you multiply that out, you end up with a cubic like you would expect, and from that cubic we can go back and construct the the third order differential equation, there is a typo here on this slide, so this should be not plain old 9, but 9x, right? That 9 in the characteristic equation corresponds to x to the 0th power in the differential equation. Okay, so differential equation with the stated general solution is given by x triple prime minus 5x double prime plus 3x prime plus 9x equals 0. Okay, one more example. Let's find the general solution of this fourth order equation, x fourth derivative plus x first derivative equals 0. Okay, so as you might expect, we'll go ahead and try a solution of the form e to the lambda t. The characteristic equation corresponding to this differential equation is lambda to the fourth plus lambda equals 0. That factors quickly as lambda times lambda cubed plus 1 equals 0. And that cubic factors 2. It turns out that the cubic factors into this form. Okay, so that's one of those sum of cubes that you may have seen before that you don't exactly remember, but that's a formula for factoring that cubic. Okay, so now it's quick to pick off eigenvalues. One of them is certainly 0, and one eigenvalue is minus 1. And there's 2 more eigenvalues that correspond to roots of that quadratic equation, which turn out to be 1 plus or minus 3i over 2. So corresponding to those 4 eigenvalues, we obtain 4 linearly independent solutions. Fundamental set of solutions is 1, right? That corresponds to the eigenvalue 0. Minus 1, the eigenvalue minus 1 corresponds to e to the minus t. And then, of course, corresponding to these complex conjugate roots, we get cosines and sines times exponentials. General solution of the differential equation is a linear combination of those linearly independent solutions, which again here I've written the cosine and sine terms in factored form, factoring out the e to the t over 2. As you might expect, a 4-parameter family of solutions corresponding to this fourth order differential equation. Okay, finally in this section we'll talk about non-homogeneous differential equations, so we know exactly how to solve linear non-homogeneous differential equations. We know that that corresponding to a linear nth order non-homogeneous differential equation Lx equals f of t, the solution ought to be x equal xh plus xp. Okay, so that's what we see here. The solution to that differential equation is xh plus xp, where xh is the solution of the homogeneous equation. So we start off the solution of this non-homogeneous equation just like you would expect, solving the corresponding homogeneous equation. After we find the fundamental set of solutions, we can turn to the particular solution, and in this case, for the particular solution, we'll go ahead and just use the method of undetermined coefficients as we've done before. So as we saw before, the method of undetermined coefficients can be summarized in one sentence by saying, let's make an educated guess for the particular solution and amend it if we need to. Okay, so here's an example. Let's go ahead and find the general solution of this fourth order differential equation, x fourth derivative plus x first derivative equals e to the minus t. Okay, so start off by solving the corresponding homogeneous equation. So the homogeneous equation Lx equals 0, we saw that the fundamental set of solutions can be constructed by these 4 functions, 1, e to the minus t, and then of course the exponentials times the cosine and sine respectively. We just went through that example. Now we'll go ahead and think about the particular solution. On the right hand side here we see e to the minus t, so we'll start with a particular solution of the form e to the minus t. Compare this to our fundamental set of solutions and notice that that's going to solve the homogeneous equation. So we have to amend our particular solution, multiplying by t again, to take our particular solution equal to a times t times e to the minus t. So we'll go ahead and just substitute that into our differential operator and try to determine how to choose a in order to pop out e to the minus t. So of course, in order to plug into our differential operator, we need the first and fourth derivatives, and I've written them here as a fourth derivative, just using the product rule a few times. And of course, here is the first derivative, just using the product rule once. Okay, so simplify, simplify, simplify. you can see that the terms with the t, e to the minus t cancel out, and we end up with a term of the form negative 3a e to the minus 3, e to the minus t. We'd like this to be plain old e to the minus t, and that can be true if negative 3a is 1, or as it turns out, if a is equal to minus 1/3. Okay, so we now have our particular solution. Our particular solution is 1/3 t e to the minus t, and we can express the general solution as a sum of the solution to the homogeneous equation plus the particular solution. So here's the solution to the homogeneous equation from before, and this is our new particular solution, xp. A 4-parameter family of solutions like you'd expect. Okay, so that's just about it for solving these non-homogeneous constant coefficient differential equations. You might expect solve the homogeneous equation first and then go ahead and just apply the method of undetermined coefficients. You might be asking, what about variation parameters? And it turns out that variation of parameters applies to these nth order equations too. You might not be surprised to hear that when you can write down a fundamental set of solutions to a homogeneous linear differential equation Lx equals 0, then the non-homogeneous differential equation Lx equals f has solution u1x1 plus u2x2 all the way out to unxn, where those coefficient functions u1 out to un satisfy u1 prime equals w1 over w, u2 prime equals w2 over w, uk prime is wk over w, and un prime is wn over w. The w in the denominator is the Wronskian, as we saw before. It's the determinant of the n by n matrix consisting of the 0th up to n minus first derivatives of those n linearly independent functions from the fundamental set of solutions. The numerator in each of those is what you would get from Cramer's rule, namely the numerator wk will just take the kth column of the Wronskian here and replace it by all zeros, and in the last row f. And you can imagine that's exactly the generalization of what we did before with Cramer's rule. Okay, so of course once you have these, you have to do you have to find an antiderivative of each of these to be able to write u1, u2 out to un, and once you do that, the particular solution is, as you might expect, that nonlinear combination of those n linearly independent functions. Okay, so again, I won't ask you to know this, but it's worth mentioning because it's a nice generalization of what we've done before. Okay, so that's it for higher order differential equations. Hope you've enjoyed this video. So long for now. Bye-bye.